No matter how far our telescopes advance, we will never be able to see the universe's origins. According to Albert Einstein, however, a recent discovery made by the James Webb Telescope has captured something extraordinary that may be closely linked to the Big Bang. Rather than to stars and galaxies, it appears that Einstein's intuition was probably correct. How can we possibly observe an event that seems to have emitted no light? Not only did it occur in complete darkness, but it was also so massive that it defies our physical comprehension. According to prevailing theories, there are questions about whether this could actually be the beginning of everything we know. This groundbreaking discovery could provide us with important answers about our existence and shed light on the conditions that prevailed in the early universe. Our universe began as a tiny point about 13.8 billion years ago. Due to a tiny irregularity, the singularity broke free from a state of perfect equilibrium and eventually developed into the universe as we know it today. Interestingly, remnants of this original point can still be found within black holes in our universe, where the gravitational forces act. These black holes are so powerful that their interiors approach infinity, confusing our methods of measurement. The James Webb Telescope, NASA's latest space observatory, has now captured images of a black hole and a vast void at the dawn of time, potentially preceding the appearance of the first stars in the cosmos. Just imagine the early universe shortly after the Big Bang. A scorching, dense mix of particles and radiation expanding at an astonishing rate. At this stage, there was no conventional light as we know it because photons, the fundamental particles of light, constantly interacted with dense free protons and electrons, unable to traverse space freely. It took around 380,000 years after the Big Bang for the universe to cool down enough to allow the formation of the first neutral atoms, primarily hydrogen and helium. As the cooling progressed, photons gained the ability to move freely, giving rise to the cosmic microwave background. However, the universe remained in darkness since there were no light sources like stars or galaxies yet. Several hundred million years after the Big Bang, the process of reionization commenced with the formation of the first stars and galaxies. These young, hot stars emitted intense ultraviolet radiation, which ionized the surrounding neutral hydrogen atoms. The ionization of hydrogen atoms resulted in protons and free electrons, increasing the universe's permeability to ultraviolet and visible light. Gravity was the driving force behind the creation of the earliest stars and galaxies, forcing gas clouds, especially those containing hydrogen and helium, to condense. Within these condensed regions, pressure and temperature increased to the point where nuclear fusion ignited in the cores of these first stars, generating light and illuminating the universe for the first time. Their radiance significantly contributed to the reionization process, gradually rendering the universe more transparent. The radiation emitted by these stars and galaxies was potent enough to ionize the dense fog of neutral hydrogen that had pervaded the universe until that point. This ongoing process persisted until the entire intergalactic medium was predominantly ionized, signifying the end of the Dark Ages and the birth of the universe as we currently understand it. Thus, even with the most advanced telescopes, our observation is limited to the point when the universe became transparent and light could freely propagate. Until now, scientists had presumed that this milestone occurred approximately 380,000 years after the Big Bang. The James Webb Space Telescope, renowned as the most advanced and powerful telescope to date, is on a mission to uncover the secrets of the universe's origins. Equipped with 16 honeycomb-shaped mirrors and cutting-edge infrared technology, this remarkable telescope captures light signals that have traveled to us for an astonishing 13.5 billion years. It has already made significant strides by discovering ancient galaxies and now has made another thrilling finding: a black hole that existed a mere 500 million years after the Big Bang. Black holes are essentially patches of immense emptiness devoid of matter, but they possess an extraordinary property, gravity, that allows them to attract surrounding matter in a seemingly magical manner. You might wonder how something seemingly empty can carry such weight. This revelation challenges our understanding of the early universe and the objects it contained. This particular black hole, though not among the largest known, is remarkably old and unusually massive, weighing in at around 10 million times the mass of our Sun. Scientists explain this by proposing that either the enigmatic dark matter or the process of black holes consuming matter causes them to gain mass. researchers have discovered an incredible black hole that is growing at an extraordinarily fast rate, leaving them perplexed as to what is causing it. If we extrapolate the growth rates observed in present-day black holes, this particular black hole would have to be older than the universe itself, which seems impossible. However, we cannot completely rule out the possibility that some elements of our cosmos existed in a precursor universe. Dark matter, like black holes, is invisible, but its presence is inferred through its gravitational effects on space-time. It is also plausible that black holes in the early universe possessed entirely different characteristics from those we have studied up close. James Webb's series of captivating discoveries have shaken established theories and exposed flaws in our current understanding of cosmology. Enormous black holes that grow at unprecedented rates in galaxies that appear to predate the universe challenge the foundations of previously accepted theories and calculations related to the Big Bang and its aftermath. Scientists now face a formidable challenge, one that may lead to a complete reevaluation of our cosmological worldview. New theories are emerging and old ones are being revisited. For instance, the theory of variable physical constants suggests that the laws governing the universe at its inception differed significantly. Fundamental physical constants, such as the gravitational constant or the fine structure constant, may have had entirely different values during the early stages of the universe. Such variations could explain the rapid growth of galaxies and the mysterious expansion of black holes. While the general theory of relativity describes forces and events on a vast scale, including gravity, the theory of quantum gravity seeks to reconcile Einstein's theory with the ideas of quantum mechanics. It is an intriguing approach that merits discussion. The field of quantum mechanics examines the behavior of minuscule particles and the forces operating in that domain during the early stages of the universe, close to the Big Bang when everything was incredibly small and dense. While Einstein's theory of the largest phenomena was primarily used by scientists to formulate the Big Bang theory and calculate the early evolution of the universe, there may have been errors introduced by this mismatch. James Webb's discoveries now provide evidence of such discrepancies. In summary, scientists are currently faced with a complex riddle that requires unraveling. Georges Lemaitre first referred to this as the hypothesis of the primordial atom. American astronomer Edwin Hubble's observations in the late 1920s revealed that distant galaxies were receding from Earth at faster speeds, meaning that the distances between them were increasing. While much of this understanding was based on observations and calculations, we now encounter phenomena that no longer fit neatly into these foundational assumptions, which scientists interpreted as evidence of the universe's expansion over time. Additional theories were then incorporated to complement these initial assumptions, ultimately shaping our cosmological worldview. Different theories exist regarding the formation of the first black holes, and scientists are actively researching this topic to gain a better understanding of the early universe. However, within these established patterns and frameworks, the precise timing of the first black hole formations remains a subject of ongoing research and exploration. One prevailing theory suggests that the first black holes formed from the remnants of massive stars known as population 3 stars, which appeared a few hundred million years after the Big Bang. These early stars, thought to be short-lived, may have ended their lives in colossal supernova explosions, potentially leaving behind black holes as remnants of their massive explosions. In addition, there are observations of supermassive black holes that existed in the early universe with masses ranging from millions to billions of times that of our sun. Scientists are still unable to explain how these black holes attained such enormous sizes in such a short period of time. This theory suggests that black holes could have formed even before the first stars under certain circumstances. Rotating dust disks that had the potential to form stars could collapse directly into black holes. According to one theory, they may have originated as a result of smaller black holes merging with larger ones as they absorb matter. However, this theory needs the existence of stars and matter falling into the black holes. With its extraordinary powers, the James Webb Space Telescope has the potential to reveal more about the early universe than any other telescope. By peering deeper into space, it can see the first galaxies and quasars, which are powered by supermassive black holes that function as a kind of time machine. The telescope gives us a direct look into the mysteries of the early universe by allowing us to examine light that was released billions of years ago. Astronomers are faced with a big mystery and the necessity to find solutions to solve cosmic enigmas. As the James Webb Space Telescope reveals the mysteries of the early universe, The mysterious creation of the first black holes presents itself as an intriguing cosmic riddle that pushes the boundaries of our knowledge and compels researchers to learn more about the mysteries that exist at the intersection of space. As we delve deeper into the universe's early stages, scientists are also exploring the impact of dark energy, a mysterious force that drives the accelerated expansion of the cosmos. Unlike dark matter, which interacts with normal matter via gravity, dark energy is thought to influence the universe on a grand scale. It is believed to constitute about 68% of the universe, but its true nature remains one of the biggest mysteries in cosmology. Understanding dark energy is crucial because it affects the rate at which the universe expands, and its properties could have significant implications for our understanding of the cosmos. Moreover, researchers are examining the implications of the multiverse theory, which proposes that our universe might be one of many universes existing simultaneously. This theory arises from certain interpretations of quantum mechanics and cosmic inflation, which suggests that different regions of space-time could have experienced varying physical laws or constants. If the multiverse hypothesis is correct, it could offer insights into why our universe has the specific conditions necessary for life and why certain fundamental constants have the values they do. Another area of intense study is the nature of cosmic inflation itself. Inflation theory, initially proposed by Alan Guth, posits that the universe underwent an exponential expansion during its earliest moments. This rapid expansion could explain the uniformity observed in the cosmic microwave background and the large-scale structure of the universe. Scientists are now looking for observational evidence of inflationary dynamics in the form of gravitational waves. These ripples in space-time could potentially reveal information about the universe's expansion rate and its conditions just after the Big Bang. Additionally, the search for primordial black holes, those formed in the early universe before the formation of stars, continues to intrigue scientists. These hypothetical objects could provide insights into the conditions of the early universe and the formation of black holes in general. If primordial black holes exist, they could contribute to dark matter, further complicating our understanding of these enigmatic entities. Researchers are employing various methods to detect these elusive objects, including gravitational wave detectors and gamma-ray observatories, hoping to find traces of their existence. In the quest to understand the universe's earliest epochs, the study of cosmic strings, hypothetical one-dimensional defects in space-time that could have formed during the early universe, also holds promise. Cosmic strings might have played a role in shaping the structure of the universe and influencing the formation of galaxies. Although these strings have not yet been detected, their potential impact on cosmic evolution makes them an intriguing subject for theoretical and observational studies. The interplay between general relativity and quantum mechanics remains a fundamental challenge in theoretical physics. Efforts to unify these two frameworks into a single theory of quantum gravity are ongoing. String theory, loop quantum gravity, and other approaches aim to reconcile the macroscopic and microscopic views of the universe. A successful theory of quantum gravity would provide a comprehensive understanding of black holes, the Big Bang, and the very fabric of space-time. In the field of exoplanet research, scientists are increasingly focused on finding planets in the habitable zones of other stars. These are regions where conditions might be right for liquid water and, potentially, life. The discovery of exoplanets with atmospheres similar to Earth's could provide valuable insights into the conditions necessary for life and the potential for finding extraterrestrial civilizations. Missions like the James Webb Space Telescope are pivotal in characterizing these exoplanets and assessing their habitability. Astrobiology, the study of life in the universe, is also expanding our understanding of the conditions that could support life. Researchers are exploring extreme environments on Earth, such as deep-sea hydrothermal vents and acidic lakes, to understand the potential for life in similar extreme conditions elsewhere in the cosmos. These investigations help refine our models of habitability and guide future searches for life beyond Earth. Furthermore, advances in computational astrophysics are enabling scientists to simulate cosmic phenomena with unprecedented detail. These simulations help researchers understand complex processes such as galaxy formation, black hole mergers, and cosmic collisions. By comparing simulations with observational data, scientists can test theories and refine models of the universe's evolution. The study of high-energy astrophysics, including observations of gamma-ray bursts and cosmic rays, provides insights into the most violent and energetic processes in the universe. These phenomena offer clues about the formation of black holes, neutron stars, and the dynamics of supernova explosions. Observatories like the Fermi Gamma-ray Space Telescope and the Pierre Auger Observatory are crucial for understanding these high-energy events. In parallel, efforts to detect gravitational waves, ripples in space-time caused by massive accelerating objects, have opened a new observational window into the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo collaborations have already detected waves from colliding black holes and neutron stars, providing new information about these cosmic events and testing predictions of general relativity. As our observational tools and theoretical models continue to evolve, the quest to understand the universe's origins and its fundamental workings remains one of the most exciting and challenging endeavors in science. Each new discovery adds a piece to the cosmic puzzle, pushing the boundaries of our knowledge and revealing the profound complexities of the universe.